All right, so let's solve some problems dealing with Doppler effect here. In this example, we have a physics professor demonstrates the Doppler effect by tying a 600 hertz sound generator to a 1 meter long rope and whirling it around her head in a horizontal circle at 100 RPM. What are the highest and lowest frequencies heard by a student in the classroom? All right, so let's kind of try to visualize this problem. One thing you can assume here is, let's say, if you have a teacher here, let's say something like this, right? So here's then the rope, and let's say here's the generator. And let's take one of the students to be somewhere right here. Okay. So teacher, and then student. Okay. Now the idea here is, as the generator goes around in a circle, something like this, that means during the rotational motion, sometimes the generator moving away from the student, and sometimes it's moving toward the student or students. That means what you have here is the times when it's kind of going parallel, or parallel to the vision of the student doesn't count. But if you're talking about like toward the students, if the student sees the generator coming toward or moving away from it, then that's when you hear the Doppler effect frequency change or apparent frequency change, right? So then we can assume that you have two scenarios. One is moving away, the other one is moving toward the student, and we can take that and we can use those two scenarios and calculate. So we are given the frequency, original frequency of the generator, which is 600 hertz. But we're not really given the velocity or the speed at which it's going around. But we are given the length of the rope, and we're giving 100 RPM, which is technically the angular velocity or angular frequency or angular velocity. But hopefully you guys remember how to relate tangential speed to the angular velocity. And because we get given the radius as well, we can easily calculate that using V is equals to R times omega. So basically we are given omega here, which is 100 RPM. RPM is not necessarily the unit that we want when we're calculating the tangential velocity. So we actually need to convert that to radians per second. But in any case, so if I plug in here for the tangential velocity, I can say, all right, so the 1.0 meter is the radius, and then 100 RPM, which technically, it can be written as revolutions per minute, revolution per minute. And then we can use this to calculate in terms of converting to where 1 minute is 60 seconds. And one revolution is 2 pi radians. Then we can see that revolutions cancel out, minutes cancel out. Radian is not a real unit. So what we end up here is meters per second as a unit that technically has a significant importance to us. But still, doing the calculation, we should get 10.47 meters per second. So that's how we would find tangential velocity. So now that we have tangential velocity, then you can assume that the generator goes around at 1 meter long, the radius, right, at 10.47 meter per second at all times. So when it's moving away from the student, it's moving away at 10.47 meter per second. When it's moving toward the student, moving toward the student again at 10.47 meters per second. All right, so applying the equations for the Doppler effect that we looked at in the previous video. So we had frequency when it approaches can be calculated as 1 over 1 minus v, which is velocity of the source over velocity of the sound in air. Then this time original frequency. So using this, we can then calculate 1 minus source velocity, 10.47 meters per second, speed of sound in air, 343 meters per second, times frequency of the generator, 600 hertz. This should give us 600, roughly 620 hertz, which you can see as the generator moving toward the student. And obviously here we are assuming that speed of the student or the observer in this case is 0. So we can kind of ignore that. And when it approaches, the frequency appears to be increasing. So the student hears 620 hertz. The instant when the generator is moving away, then we can use the equation where it's plus. The difference here is that, right? Velocity of the source divided by velocity of the sound times the original frequency. So then what we end up here is 1 plus 10.47 meters per second over 343 meters per second. This whole thing then times 600 hertz. So here we should get then roughly 580 hertz, which should, which would make sense because when object moving away from the observer, the frequency appears to be decreasing. So that means during the rotation of the generator, the student or students hear those two highest and lowest frequencies. Okay. 620 hertz, highest, 580 as the lowest. All right, so let's look at another example here. So we have a driver travels northbound on a highway at the speed of 25 meters per second. A police car traveling southbound at the speed of 40 meters per second approaches with its siren producing sound at the frequency of 2500 hertz. All right. So we're given both the driver, which has a, who has a speed of 2500 meter per second, and police car moving at the 40 meter per second. So we have both the source and the observer moving relative to one another. And we can say then the original frequency, right, the siren producing sound at the frequency of 2500 hertz, that's the frequency, actual frequency of the, let's say, police car. That means we can say that 2500 hertz is our original F. All right, so from here, what we can do, we can just write down the information, velocity of the object. Right now, I'm just writing down the speed. So it's given as 25 meters per second. Velocity of the source is given as 40 meters per second. And original frequency as 2500 hertz. Okay. Now, part A is asking what frequency does the driver observe as the police car approaches, right? So that means because we know that driver travels northbound and police car southbound, they're approaching to one another. So we can kind of use that information to calculate the apparent frequency heard by the driver. So let's go to the next page here. So again, writing down the information. So the speed of the observer is 25 meters per second. The speed of the source is 40 meters per second. And then original frequency here is 2500 hertz. Okay. Now for part A, so what we have here is, let's say that this is the driver, like D for the driver, or like O for the observer, moving northbound. And then here's the police car, which is basically our source, moving toward the observer, southbound. So in this case, what we can do here is using the equation where apparent frequency is equals to, then because both of them are moving, I'm using more general equation where it's v, which is the speed of sound in air, plus v of the observer, then divided by speed of sound in air, then minus v of source, and times the original frequency. There you go. All right. So this is then the equation that you can think of, like, let's say that general equation that we can write it down. Then I can say, all right, so f of prime is equals to 343 meters per second. That's for the speed of sound in air, plus, now what I have here is, if I'm then looking at the signs for the observer velocity and source velocity, I have to look at it in terms of this, remember. So if they're approaching toward one another, then their velocities are positive. That means here I just write down 40 meters per second for the source. Oh, sorry, this is the observer. So 25 meters per second for the observer, and then 343 meters per second, and then write down negative. Again, then the negative is part of the equation, but because the source is moving toward the observer, we take that speed to be positive, and that becomes positive 40 meters per second. This whole thing then times 2500 hertz. Okay. Plug in, calculate. We should get then 3040 hertz or 3040 hertz, or roughly 3.04 kilohertz. Remember, so technically I can write this one as 2.5 kilohertz. All right, so this was part A, where they are approaching one another. Now, if we go back and look at part B, it says, what frequencies does the driver detect after the police car passes him? Okay, so that means what we can do here, we go back and we say, all right, so let's look at part B. That means, as they move towards each other, obviously this is not a collision, right? It's just basically thing like this, right? So at this point, the observer still goes northbound. And then what we can say is that, like, let's say then the source or the police car is moving southbound, continues moving southbound. All right, so then using the same equation, V plus VO divided by V minus VS times original frequency. Now, what I do this time is it's 343 meters per second plus, but you can see, right, the source is moving away from the observer. That means, or observer moving away from the source, because both moving away from each other, that means every time something moving away, the speed is, velocity taken as negative. So the observer is moving away from the source. So we write down negative 25 meters per second. Then here, 343 meters per second, then minus. Now I look at source. Well, source is also moving away. That means it's minus 40 meters per second. Then the whole thing is 2.5 kilohertz. Plug in, calculate. We get 2.08 kilohertz. So that's the answer for part A. This is the answer for part B. Okay. All right, so let's go back and look at part C. Part C says repeat parts A and B for the case when the police car is behind the driver and travels northbound. Okay, so let's see what we have here. Coming back, and I always try to do a sort of like a rough sketch like this. That means taking this to be the observer, northbound as always. But then police car initially is also northbound. So here's then the source. Okay, so now what we have here is, remember, the still same 2500 or 2.5 kilohertz, same speeds and things like that. Now, if I'm calculating this for this, let's say, scenario, F prime equals V plus VO over V minus VS times original frequency. So what I have here is 343 meters per second plus Now what I have here is, I want to now calculate write down the speed or the velocity of the observer. Well, observer is moving away from the source. So again, moving away from the source means that negative 25 meters per second velocity. Then here, 343 meters per second, minus. Then what I do, I look at the source. Well, source is moving toward the observer, so its velocity is positive, so 40 meters per second. This whole thing times 2.5 kilohertz. The answer then will be 2.62 kilohertz. Okay, again, this is while police, both of them moving northbound, but the police is behind the driver, right? And moving toward the driver. So let's say, I don't know, let's say put A prime, right? Which is the, this part A, but kind of like modified. And then we have like a B prime, where we're saying that, okay, now the police car basically catches the, or overcomes and then just moving ahead, right? So it's just, let's say if this is now observer still moving northbound, but then it's behind, let's say the police car. So that means here's the source. That means this is basically this last scenario that we're looking at. So F prime here is equals to, I can just write down the equations. You already know the values, you already know the equation. So this will be 343 meters per second. Then plus, now if I look at the observer, hopefully you can see observer moving toward the source. So it's 25 meters per second. So positive 25 meters per second. Then 343 meters per second minus, but this time the source is moving away from the observer. So minus 40 meters per second. All right, then 2.5 kilohertz. Plug it in. The answer here is 2.4 kilohertz. And that's the answer for this modified part B. All right. So one more example dealing with Doppler effect. So here we have an interesting problem because you're going to see that this is slightly different. So we have a bat moving at 5 meters per second is chasing a flying insect. If the bat emits a 40,000 or 40 kilohertz chirp and receives back an echo at 40.4 kilohertz, what is the speed of the insect? And basically based on that, will the bat be able to catch the insect or not? So the difference here is that what we do here is we have a source that emits a sound, and then we have an observer. But then what happens here is then there's an echo. So then original source basically becomes then observer for the echo. So we kind of have to we have two parts. So you can, break it down into the observer, first observer is the insect, source is the bat. Then on its, for the echo, it's other way around. Basically the insect is the source and the bat is then the echo. The bat is then the observer. So let's kind of look at it. So here's, I'm going to put B for the bat, and the bat basically is moving with the 5 meters per second. So that's we're given. You want to put in terms of let's say 5 meters per second I had. We can also kind of do it like that. And let's say somewhere over here is the insect. Insect is moving again with the speed. We don't know what it is, but some kind of horizontal speed. Just make it simple and just assume they're moving along the horizontal axis. Right now, what I have here is I don't know what the value of the insect velocity is. I don't know what is the speed, in which direction it is moving, but we can, from the problem, we can see, right? It's chasing a flying insect. Obviously, the insect is not going to be moving toward the bat, right? So, I mean, at this point, there's a chase, right? And we assume that insect is moving away from the, let's say, from the bat, and bat is pretty much chasing the insect. What we can see here is, let's say, part one, where we can assume that here's the bat moving in this direction, and this is basically the source, right? So bat is the source. And then the insect, so basically for the insect is the observer. So I'll put like this. So this is the observer. Again, the speed here is 5 meters per second for the source, and observer speed is unknown. The frequency, and again, I'm doing the first part. The frequency, original frequency, is 40 hertz. Okay. Now, I can write down the equation for part one. So this will be then F prime is equals to, again, both are moving, so I can just write down the general equation for this. And the general equation will be V plus VO. Well, in this case, let's say I can just put Vx, right? And this is over V minus V source. And then times original frequency. Okay, so this is for part one. Then let's look at part two. If you want, you can just plug in some values, right? So this is what? This is 343 meters per second plus Vx over 343 meters per second, then minus, well, what we have here is we have bat moving toward the insect, so this is going to be then -5, right? Meters per second. Okay. Now, another thing I know here is if I'm following what I kind of going over, in the previous few examples, we can see that insect is moving away from, it's moving away, right, from the bat. So that technically then I can come back here and then put this as negative. Okay, I don't know the value, but I know that basically it's moving, so that will be some kind of minus some number. And this is all times 40 hertz. All right, so then I have part two. So part two here is, what I have here is, like, let's say sound travels to the right, basically hits the insect, then comes back. Now, basically we are going back, right? So that means the echo is coming from the insect. So the insect basically is the source. So let's say here's my source. And then here's my observer. So for this one, again, insect is moving to the right. And what I know here is now I know my velocity of the observer, which is then 5 meters per second. All right, so, and again, obviously, Vx here is, unknown for the source at this point. All right, so what I do here is, let's call this F double prime. So then I can say that this is equals to, all right, so V plus Vx over V minus Vs times, and the frequency that coming back, which is basically going to be frequency F prime. So it's going to be this particular frequency. Okay. Now, if I write this down, then I can say this is 343 meters per second. Then I want to know, okay, so, sorry guys. So this will be, well, sorry, that was the general equation, but still, in the equation V plus V, this will be observer. In this case, is the actually, do it like this, right? So 343. Well, my observer here is the bat, and the bat is moving toward the source. So it's basically plus 5 meters per second. Then this is over 343 meters per second minus Vs. Well, minus, and I know that in this case, source, which is the insect at this point moving away, so it's going to be some negative number, so I can just put plus Vx. Okay, and times F prime, and let me just put it like this, F prime. All right, so now what we end up with here is this, right? That means F double prime is equals to So then I have 343 meters per second plus 5 meters per second. Let me just ignore, the units, not the units, like let's say sig figs, but let's put that actually meters per second, then over 343 plus Vx. Then what I do here is it's F prime, but then for the F prime, I'm going to go ahead and just bring this here. And we say that this is, basically same as 343 meters per second minus Vx, then 343 meters per second minus 5 meters per second times 40 hertz. And that's what I have. Then from here, we just basically do, that will be, kind of easy to just combine terms that we kind of know. That means, we can just rearrange it where it's 343, let's say plus 5, just to save some room, 343 minus 5, then times 343 minus Vx over 343 plus Vx times 40. So if you kind of put it like this, then just basically we know one thing for sure is that F double prime is the frequency of the echo, and we know that that frequency is 40.4 kilohertz, the apparent frequency of that. That means if I come back here for F double prime, I can say that is 40.4 hertz. That means at this point, I know everything, as you can see, right, in this equation, except Vx. So we can just, do a little bit of algebra, which, I'm confident you should be able to do that. Do some algebra and calculate the Vx. You should be able to then get about 3.29 meters per second. This will be then the speed for the insect, and obviously, we know that's since technically it's going to be positive, it's going to be in the direction that we calculated or assumed to be, which is to the right. And you can see, right, if the bat is moving at 5 meters per second, an insect is only 3.29 meters per second. Clearly, part B says, will the bat be able to catch the insect? It will be able to, because there's a difference, right, of the speed between them. It's roughly 1.71 meter per second difference, where bat is moving faster, by that much. So clearly, it will catch, the insect eventually. All right. So this was this particular problem. So for the problems when there's an echo, the best way is just basically to break it down to just two parts, and kind of like writing down the equation for each part, where then technically then this F prime is basically the equation F prime from the first part. That means apparent frequency in the first part for the original, like let's say chirp, ends up being the let's say frequency coming, when it's echo, right? F prime is basically the original frequency for part 2 when it's coming toward the, coming back toward the bat. All right. So the next concept here, we have a superposition of sound waves. So one of the things we're going to be doing here, kind of similar to things we covered already, to look at constructive destructive interference, to superposition of sound waves, when let's say you have speaker, or a couple of speakers that let's say generate sound and traveling along some path. So here, let's say we are given a speaker, which we can represent it as S. This is like the source of the sound waves that we have. And in this picture, you can see, right, when you're generating sound, we're giving you two different paths to go. So we have at point P, they then have two paths. So we can go path R1 or path R2. So what we can think of here is when the sound here separates into two. So let's say some of them kind of go like this through the path length of R1 and reaches position Q. And then we have, the half, the other half, right? Kind of like, like let's say breaks into two parts, right? And what travels technically is the energy information, because remember the all the waves are basically just pure energy, right? So that means you can think like each wave represents half of the energy, right? Half of the energy that was available at point P before they got, kind of like separated into two, because we have like a junction over there. And then, you go path length R1, and then other half go path length R2. And then they get to position Q. They come back, right, to position Q. Now, the idea here is that when they get to position Q, then basically we combine. If they are basically traveling, if they travel, for example, exactly same length R, then they will combine again, same way, and will generate what we call, constructive interference. But they, if they happen to go different path lengths, then things can be a little bit different, right? That means, for example, the second wave can reach position Q at a different, what we call phase, right? I mean, let's say crest is it would have been constructive, but for example, if it's crest and trough, or any other combination, then you can get some difference in the frequency, right, in the pitch of the sound. So the idea here is we're going to be looking at some problems like this, right? So you have let's say two waves. So one wave is traveling path length R1, the second one traveling path length R2. And one thing we have here is when they reach Q, they combine, and what basically goes to R will depend on their phase difference. Okay, so one of the things we can see here is the mathematical approach for this will be more or less something like this. So taking the one wave to be Y1, another wave to be Y2, and we put it as like A sine kx minus omega t. Second one, Y2 equals A sine kx minus omega t plus phi, assuming that, let's say, there could be potentially a phase difference between them. When they get to point Q, right, they combine to create, another wave, right? It's basically superposition wave. So that means what we're doing here, we're just adding them together to get this wave Y, okay? And one of the things we can do here is, what we're saying here is this is equals to A sine of kx minus omega t plus A sine kx minus omega t plus phi, the phase constant. Okay, so basically we're adding two waves together. Now, whenever you have something like this, right, so you're adding two sine functions, so we have to go back and look at some of those trig identities, and we have this particular trig function, let's say algebra, where sine of A plus sine of B, the solution of this is 2 cosine A minus B, where A is assumed to be the argument of first sine function, B is the argument of the second sine function, so it's A minus B over 2. So this is a cosine, so 2 times cosine of A minus B over 2, then times sine of A plus B over 2. Okay, so that's kind of what we end up. That's just general rule. You learn this in trigonometry class. So, and that's what we're going to be applying, because what I have here is I can say that my A is equals to kx minus omega t. My B here is kx minus omega t plus phi, and I just pretty much plug in into this equation and calculate. So if we do that, so then we're going to have y is equals to, and so one thing we can do here is A is the amplitude right in front of the sine functions. So probably before doing this calculation, we can just factor it out. So then we have just pure sine function. So that means what I have here is that I have A times then that, right? So it's just basically 2 cosine, and then I have A minus B. So this will be kx minus omega t. Then minus, then it will be kx minus omega t plus phi. This is divided by 2. Then sine of kx minus omega t, then plus kx minus omega t plus phi. This whole thing divided by 2 again. And then we can just calculate from here, right? Y is equals to 2a, combining those two, then cosine. And then from here, we can see if we do the little algebra, right? So this technically cancels with that. This then cancels with that. And we only have phi inside there. That means I can just say this is cosine of phi over 2. There. So therefore, then the second term, I can see that basically I have two. So it's kx minus omega t minus kx. So it becomes 2kx minus, I have omega t, another minus omega t, kind of like this, right? So 2 omega t, then plus phi divided by 2. So the finally we have then 2a cosine phi over 2, then sine. So for example, this term divided by 2 just going to give me kx minus second term divided by 2, going to be omega t. Then finally the third term divided by 2, then plus phi over 2. And that will be our final expression, right, for the superposition of the sinusoidal waves. All right. So we end up with this particular equation. Then you can think of, let's say, what I have here is if you have two sound waves, traveling at, let's say, two different paths, and R1 being path 1, R2 being path 2, then one of the things we can look at it here is the path length difference. That means delta R, the difference between those paths, which is just, R2 minus R1. And then what I get here is that, this delta R, which is R2 minus R1, is equals to then n times lambda, where n here is equals 0, 1, 2, 3, and so on and so forth. That means what I have here is, I can then just basically relate the path length difference to this particular equation and to the wavelength of the waves. All right, so we can see that, for example, here there's a picture of that. Now we can get some special cases, right? Special case, because one of the things we can see here is, as I mentioned, right? So depending on the path length difference, you can have those two waves being in phase or out of phase. So then one of the things we can see here is, let's say, for example, here the individual waves are in phase and therefore indistinguishable. Constructive interference, the amplitudes add. Okay, now what are the conditions for us to have, let's say, constructive interference? Well, we can see that right now, when you have, let's say, this term where you have cosine of phi over 2. So this term is basically going to determine, so this what we call technically the amplitude of the wave, which is the superposition wave, like this, right? So as you can see, right, that amplitude of the superposition wave is equals to 2a cosine phi over 2. So the maximum for this is when this amplitude of the superposition wave is equals to 2a. Okay, so in order for it to equals to a is the amplitude, right? I mean, it's a, you can't really do anything about it. So a is the amplitude of the waves. So that means you have to look at then the cosine phi over 2. So then what we have here is when cosine phi over 2 as a term equals to 1 or -1, then you technically get maximum amplitude for the superposition wave. That means it's equal to 2a. That means when cosine of phi over 2 is equals to plus minus 1, then you get, the constructive interference and amplitudes add. Well, for that to happen, the feed with phase constant has to be 0, 2 pi, 4 pi, and so on and so on radians. That means if you have 0, then cosine of 0 over 2 is 0, cosine of 0 is 1. If phi is 2 pi, then you can see, right, cosine of 2 pi over 2. Well, this gives you then cosine of pi, and that's equals to -1, which is, something that acceptable for this particular case. That means +1 or -1, and then you go to 4 pi, becomes +1, then and so on and so forth. So, and every time you basically have standing wave generates, so just basically giving you a constructive interference, right? Those two waves, combined together. Okay. So here, as you can see, an example of that, right? So if phi of original wave equals 0, then cosine of phi over 2 equals cosine of 0 equals 1. And amplitude of the resultant wave equals 2 times a, twice the amplitude of the either individual waves, and can occur when the difference of path length is equals to 0, because what I have here is, delta R is equals to R2 minus R1. If R2 minus R1 gives me 0, that means R2 is equals to R1, right? So if R2 minus R1 is 0, it only can mean that R2 and R1 are the same, so they have exactly same path length difference. And you get that. That means what we have here is, we can say that delta R is equals to then n times lambda. So then where it's basically end up with some integer multiple of wavelengths. That means you can say that, n can be like 0, 1, 2, 3, and so on and so forth. And that's going to be then depend on the values of R, the R2 minus R1 that we get. All right, so that's kind of what we have. That means the crest of two waves at the same location in space, and waves are in phase. So you get constructive interference, and you can more or less assume that, same thing can occur for the, 2 pi, 4 pi, and so on and so forth. Obviously, then we can have, when phi here is not, let's say 0, 2 pi, 4 pi, and so on and so forth. Why if it's pi? Well, if it's pi, then amplitude of the standing wave, a superposition wave, is equal to 2a cosine pi over 2, and we know that cosine pi over 2 is 0, so 2a times 0, we get 0, which means that this is y1, this is y2, and if they are out of phase by pi radians, which is 180 degrees, then what you get here, when you add them together, you get 0, which makes sense, right? Because one has a positive amplitude, the other one has a negative amplitude. So when you're adding them together, you get, 0. Let's say if the amplitudes are exactly the same. So so then this line over here represents that, the superposition wave, where in this case it's 0. That means you can think of it, that's kind of like what can happen. That means cosine of phi over 2 equals 0 when phi is equals to pi. Same thing can happen when it's 3 pi or 5 pi, and so on and so forth, right? That means the crest of one wave occurs at the same position as the trough of the second wave. You can see in the figure, and then occurs when path length difference are, let's say this delta R, right, is lambda over 2, 3 lambda over 2, and so on. That means you can look at it in terms of this, right? So calculate delta R, for example, and if you get then out of phase, then it's not going to be, let's say, n times lambda. It will be in terms of lambda over 2, or 3 lambda over 2, and so on and so forth, or basically n times lambda over 2. So where n here is going to be an odd number, right? So 1, 3, 5, . All right, so now what, in a way, this represents here is when you have source 1, for example, and you have then the source 2. So let's say if you have some position that you're considering, position P, when the waves reach that position, let's say, so this is, let's say, R1, this is R2. So then if you do R2 minus R1, you don't get basically, let's say, an integer. So what you get here is you get some kind of fraction. That means what they have here is they're not separated by, one wavelength, because what you have here is two waves, if you kind of put them together, like let's say here's a wave, and then second one, let's say goes like this. And let's you can assume that they're continuing, right? So those are two waves that are in phase. But see, if I take one of the waves and shift it by exactly one wavelength, it's still in phase, because what I have here is crest, crest, trough, trough. The just difference here is then delta R is equals to 1 times wavelength. There's a 1 wavelength difference between them. That means this is how much this one has to travel, R1, this is how much this one has to travel, R2, and it's exactly 1 wavelength difference, 1 wavelength equivalent distance difference between them. Same thing you can say, right? If I have 2 wavelength difference or 3 wavelength difference, so on and so forth, right? So that means they're still going to be in phase. So that's why delta R is equals to n times lambda. We know n is 0, 1, 2, that doesn't matter, right? When n is 0, that means R1 and R2 are exactly the same. That means this point P is exactly between them or something like that. So they travel, both waves travel exactly same distance to reach P. But as long as this is true, you get constructive interference. That means two waves have exactly same number of wavelengths when they reach P, or one is longer by exactly 1 wavelength, or by exactly 2 wavelengths, or exactly 3 wavelengths, you still get constructive. But here what we're saying for this scenario is that R2 minus R1 is not equals to 1, let's say 1 times lambda or 2 times lambda is a fraction. Maybe when it reaches, for example, here's a wave 1 and here's wave 2. If I shift this one by not 1 wavelength, but let's say half a wavelength, that means, like let's say what I get here, move this one like this, you can see, right? So just by shifting exactly half a wavelength, I get something like this. Okay, so you can see, right? And that means what you have here is it's, and when n is 1, right? Basically the first, let's say time you get this, you get exactly 1, half a wavelength difference between them. And then I can shift then 1.5 wavelength shift or 2.5 wavelength difference, and so on and so forth. So that's basically what we end up with, when the superposition waves combine, right? The waves combine and they are out of phase. Okay. So the resultant wave is 0 amplitude, which you can see that, red brown line in this diagram right here. Oops. All right. So in any case, you have then what we just discussed are 2 extreme cases. That means where both are completely in phase or completely out of phase, but you can have something in between, right? So you can have, so phi is not, a 0, or not 90 or something, right? So or 180, right? So you can have somewhere, 60 or 40 or 30 or something like that. In that kind of general case, then you can say that they can either be, you can say, right? So here's first one, here's the second one. So technically they can add up to something. It's just the difference here is that the amplitude is not double, or than the first one. So you do kind of have some kind of intermediate result, which can be neither fully constructive or fully destructive, right? It's somewhere in between. All right, so kind of finalize this analysis model. So you can see, right? So you have 2 waves. So what you get here is you can always look at it in terms of you adding 2 waves together. You have, like, let's say in the diagram here, green and blue waves are your, let's say, 2 original waves, y1 and y2. And then whenever they're interacting, right, so you get basically the superposition, right, between them. So, and what you get here is the brown is basically where represents the superposition, y1 plus y2. So you can see, right, so here's this one plus that one, and this is just basically, the superposition of them. So, and you can see that technically then you can have a constructive interference, or you can have a sort of like a destructive interference where they kind of, destroy each other, because here's the, let's say blue, here's the green, and, basically this superposition here is less than for example, in some kind of individual, individual wave, where here the brown here is greater than individual waves, where you adding them up, where here green, blue combined, but because green has a greater positive amplitude than blue has a negative amplitude. So you still get constructive, but it's just basically a little bit less, right? So it's a little bit less than what you would have had if both were positive. So you can see, right, this one here is just basically sum of the Y2 and Y1. It just happened to be Y1 was negative, so you're just subtracting them to get this particular phase. All right, so let's look at a couple of examples on this. So we have example where we have two speakers and they're driven by the same source. Okay, so we have two identical speakers, loudspeakers placed 3 meters apart. That means this distance here between them is 3 meters, driven by the same oscillator. A listener is originally at position at point O, located 8 meters from the center of the line connecting the two speakers. The listener then moves to point P, which is a perpendicular distance 0.35 meters from this position O, and she experiences the first minimum in sound intensity. So what is the frequency of the oscillator? All right, so well, one thing we have to do here is basically just use the numbers that are given to us, right? So we know that here we have a diagram already with some of the values that technically we need. But one thing you could have done here is you can say, okay, so if you start from the scratch and you're not given the picture like this, so you can say, all right, so let's take this one to be source 1, let's take it to be source 2. And then what I have here is then that this is the distance between them, which is 3 meters. And then I know that if I go exactly from the center, right, 8 meters from the center, then we get to position O. Okay. All right. So, but then what I have here is this, listener goes from O, 0.35 meters, right? 0.35 meters, perpendicular distance points out from O. That means kind of like, let's say, from here to right there. So let's call this position P. This is then 0.35 meters. Okay, that means that's kind of what we have. Now, if this is 3 meters, then technically this would have been 1.5. This would have been 1.5. Okay, but now what I have here is because she moves 3 meters, now I can draw a line like this to there, right? So they can this is still 8 meters, but then, so let's say this distance from there to here is 1.85 meters. Okay. And obviously, then this one will be 1.5 minus 0.35. So what we have here is then we can say, all right, so using all that information, I can see that source 1 has to travel this distance. This is R1, and source 2 has to travel that distance, which is R2. Okay. So that means, what I have here is we just constructed, let's say a triangles where we can find that particular information by calculating R1. And you can see, right, this is not one-dimensional, it's two-dimensional. So what I have here is I want to calculate R1, where I'm saying that this distance, for example, is 8 meters. And then this distance is technically 1.5 minus 0.35, right? So which technically will give me 1.15. That means for R1, then I can say that, R1 is because of the, what I'm given here is the adjacent side and then the opposite side, and I'm technically calculating the hypotenuse. So this will be then square root of, my adjacent side is 8 meters. And my opposite side will be then the, 1.5 minus 0.35, so 1.15 meters, and I square both. So we're going to get 8.08 meters. So that's going to be then R1. Same way we calculate R2. We can see that what I have here is basically it's 1.5 plus 0.35, right? So it's then 1.85. This is still, 8 meters. So then it's going to be same 8 meters plus then 1.85 meters square. All right, so calculating this, we get 8.21 meters. That means I got my R1 and R2, and already you can see, right, they're not the same. So I'm not going to get, for example, that particular wavelength, which is, like, let's say when R1 equals to R1 and R2 are equal to one another, delta R equals 0. But still, right? So from here, I can then take that and calculate, let's say the wavelength. So now we are told that she experiences the first minimum. What is a minimum? It's a destructive interference. First means n equals 1. That means delta R is equals to n lambda over 2. N is equals to 1. So it's lambda over 2. So lambda equals 2 times delta R, which is 2 times 8.21 minus 8.08. So lambda equals 2 times. So their difference is 0.13 meters. 2 times that, 0.26 meters. So that's my wavelength. So then I can calculate frequency. Well, what I have here is, this is sound and traveling at 343 meters per second. So frequency is equals to speed over wavelength. So 343 meters per second divided by 0.26 meters wavelength. So we get 1300 hertz. So that will be then the answer for this particular frequency. So for the next one, we have, what if the speakers were connected out of phase? What happens at point P? Now we know that they were connected in phase, but at point P, we had then the minimum, which is destructive interference. So if they were connected out of phase, then that will kind of cancel out the destructive and will make it then constructive. That means you will have a maximum rather than minimum. So because they were in phase and you got destructive at point P, if you change them out of phase, then what you get here is you get then the constructive. All right, so one more example over here. So you have two identical loudspeakers are placed on a wall 2 meters apart, kind of similar to what we had. So listener stands 3 meters from the wall directly in front of one of the speakers. A single oscillator is driving the speakers at the frequency of 300 hertz. What is the phase difference in radians between the waves from the speakers when they reach the observer? Again, kind of similar thing. Here's source 1, here's source 2. So we're told that they are placed 2 meters apart. And the listener here is 3 meters from the wall directly in front of the one of them. So we can just place them here. That means what we want to know here is what is the phase difference? That means we can assume that this one travels the distance R1, this one travels this distance R2, and R1 is then equals to 3 meters because that's the directly, direct line from there to here. All right, so one thing we can then just very easily do here is do this calculation. So since we know R1, which is 3 meters, we can just calculate R2. So as we can see, this is the distance that is R2. So R2 will be then square root of 3 meters squared plus 2 meters squared. Then to find delta R, we'll just do R2 minus R1, which is 3 meters squared plus 2 meters squared, which is R2, and minus R1. So this should give us 0.606 meters. Now, since we are given the frequency, and again, of course, this is sound wave. We know the velocity, which is 343 meters per second. We can use that information to calculate the wavelength. So wavelength is V over frequency. Again, using the equation sound, any wave velocity equals wavelength times frequency. So wavelength is velocity over frequency. So we can calculate this as 343 meters per second over 300 hertz, which gives us 1.14 meters. That's for the wavelength. Now, what we want to do is then to use the delta R equals N times wavelength. So then technically what you want to know here is it N or, N over 2, whatever it is. Remember, N and N over 2, those are the extremes. Most of the time it can be somewhere in between. So what we can do here is we can take the delta R divided by wavelength to find the coefficient in front of the wavelength in that equation. That means if I do 0.606 divided by 1.14 meters, what we're going to get here is 0.530. So it's unitless, but one of the things we can do here is we can see that information then can be used to calculate the phase difference in radians. Remember, radian is not a real unit. We just put next to a number to, kind of like represent some kind of information, because we are used to having a unit next to some number to have some kind of significant importance, right? So some kind of physical significance for the number. Otherwise, any number without a unit doesn't really, give us any information. But even if it's a radians, we know what we more or less talking about. So then what we can say here is then phase difference will be then 2 pi times then this number that we calculated, which is 0.530, and that it will be equals to 3.33 radians. And that's the phase difference in radians between the waves from the speakers when they reach the absorber. All right, so the last couple of things, last couple of concepts we're going to talk about here is going to be shock waves and sonic boom. And this is, as we talked about, moving object can create this Doppler effect. And here we have an example where if you have a source generating a wave, then you can say, right, if the object is at rest relative to the source, then you basically have no effect. Then what you have here is if object is moving and let's say generating source, right, with respect to the creating wave, comparing to the speed of sound, so velocity of the object, let's say moving object, is less than the speed of sound. So basically what we get here is we get Doppler effect. Until at some point we can then have velocity of the object equal to the velocity of the sound, or sometimes even exceed velocity of the sound. And that's kind of what we have right now. You can see, right, if a source is moving faster than a wave speed in medium, waves cannot keep up and a shock wave is formed. And equation, you can see, right, is pretty much, using simple, geometry over here. We can see that sine of the angle theta over here is then can be calculated as a ratio of the velocity of the sound divided by velocity of the moving object. So we have another that can be kind of compared to the shock waves analogous to the bow waves, which deals with the object moving with respect to the water waves. And what we have here is you can see that if object is moving faster than the water wave, the surface water waves, you have very similar effects. So like this V-shaped effect as well, created here for the faster than waves, object speed. All right, so as you can see here, there is an example where you have an aircraft that exceeding the speed of sound in air and produce two sonic booms, one from the front and one from the tail. So remember that generally, this is dealing with a lot of energy, especially when you have aircraft moving at the supersonic speed. So then what we can think of here is generally they're not necessarily, pleasant to hear, they're relatively unpleasant to hear. And that is why sometimes when you have a very fast moving, aircraft, the sound coming out, you can see over here, right, can be pretty unpleasant. So hopefully the height, the altitude of the airplane can kind of compensate sometimes for that. And here's an example that we can see for the sonic booms. The airplane is moving and generating the booms. So let's look at an example dealing with this type of scenario. So if a supersonic plane flying due east at an altitude of 15 kilometers passes directly over point P. The sonic boom is heard at point P when the plane is 22 kilometers east of point P. What is the speed of the supersonic plane? All right, so as you can see, right, so we are given some geometrical numbers that over here, we can construct the right triangle. We can see that relative to this point P, we have 15 meter height, 15 kilometers height. And we're also told that, you hear the sound when the plane travels 22 kilometers east from that point, which is, we can kind of represent it in terms of a triangle like this. And angle theta, pretty much, which is same as this one over here, right, can be just calculated using the values of the distances that we're given right now. So since we're given the 22 kilometers, which is adjacent of that triangle, and 15 kilometers, which becomes the opposite, to find this particular theta here, we can calculate using tangent of theta. So tangent of theta, remember, it's equals to opposite over adjacent. In this case, opposite is 15 kilometers. Adjacent is 22 kilometers. Units cancel out. And using that inverse tangent, over 22, we should be able to get 34.3 degrees. Now, for that, then to find the speed, we can then assume that whatever speed it has, so let's take this u to be the speed, it is basically moving at that speed when it's covering that particular distance. So we have, similarly, we can use again, trigonometry here to calculate the speed of the supersonic plane. We can assume that the time interval is the same for both plane and the sound. So by the time the sound reaches point P, is exactly the same time as the plane covers that 22 kilometers distance. So we can represent this as sine of theta equals V delta T, which is pretty much, V delta T, remember, represents the distance. So this is a distance that for the sound to reach position P, divided by then distance that is covered by the plane, which is, let's take U to represent the speed of the plane. It'll be U times delta T. The delta T is exactly the same for both. We can cancel out, and we can then calculate this, where then U is equals to V over sine of theta. Taking then this to be the 343 meters per second, which is the sound speed, divided by sine of 34.3 degrees. Then we can calculate for the speed of the plane to be roughly 610 meters per second. All right, so the last couple of applications more like, for your information type of thing. We're not going to be really doing anything with this, but you can see that sound waves can be used to some really useful applications. Let's say sonar is used to locate objects underwater by measuring the time it takes a sound pulse to reflect back to the receiver. That also actually used to provide us with some information about the structure of the planet. So because not necessarily even Earth, any type of celestial object, including the sun, any information about the internal structure of the celestial object, we usually get that information using the some kind of a wave or sound wave most of the time that can be sent and eventually receive the reflection of that or echo of that, and that can provide us with useful information. Generally, it uses ultrasound waves. Remember, ultrasound wave is the wave that is above 20,000 hertz. Human audible range is from 20 hertz to 20,000. Anything less than 20 is infrared, infrasound. Anything above 20,000 is ultrasound. So same can be also be used, some ultrasound for medical applications. So you can see that for medical imaging, it's very useful because it can easily go through the skin, let's say, and then if you have some kind of organ inside body, you want to get an image of that, you can just basically use sound waves. And because sound waves are not necessarily dangerous for our body because they don't necessarily have a lot of energy associated with them. For example, X-ray can be rather dangerous, so you don't necessarily want to do X-ray every day. But ultrasound is rather safe, and most of the time ultrasound is used to provide an image of a fetus. So here's a picture where let's say ultrasound was used to provide an image of a baby, and you get rather amazing detailed images out of the ultrasound. All right, so that's about it for this chapter, guys.